Hi, we're Group 28. I'm Matthew Sloss.
I'm Jesse Wilson.
And I'm Scott Harpool.
And this is our video presentation of our project. Our project is a multi-channel, digitally controlled audio amplifier that is both intuitive for the end user as well as very powerful for those who like their music loud. And now to Scott for our overall block diagram.
Thank you, Jesse. As you can see, we have displayed here on the board our top-level black box diagram. This is a representation of the inputs and the outputs to our system. We have 6 inputs and 2 outputs. The first input is the end user. This is the person who is actually going to be turning the knobs and pushing the buttons and listening to the music from our system. Then there is the wall outlet, which provides 120 volts AC to the system. We will detail this later, but we will also be drawing 9 amps from the wall. The next is our coaxial cable input. This is the digital audio input to our system, followed by our multi-channel RCA input, which is our 6-channel, or 5.1 if you will, analog input into our system. Then we have our 1/8 inch auxiliary cable input, which is your standard headphone jack cable that you can plug into a computer so you can play music from, say, your laptop on our audio system. And then we have our RCA cable input. This again uses RCA cables like our multi-channel input, except this time there are only 2 RCA cables for stereo input, left and right channels. And then we have our output with the environment, which is the end user's ears listening to music, and our power status indicator, which shows, do you have the system amplifiers turned on? Yes? Okay, there is a nice bright orange LED that tells you the system is on. Matthew Sloss will now go ahead and detail the engineering requirements.
Thanks, Scott. The first engineering requirement is that our case be no larger than 17 inches by 24 inches by 8 inches. This engineering requirement was passed. The second engineering requirement is that our system be able to take in a digital input and reproduce it as an audio input. This engineering requirement was not passed. The third engineering requirement was that our system be able to have an equalizer which affects a center tone frequency by plus or minus 6 dB. This allows for tone control in our system. This engineering requirement was passed. That same equalizer must also have 3 bands of tone control. This requirement was also passed. The end user must be able to digitally select which input the system takes in. This engineering requirement was passed. For safety purposes, the system must not draw more than 6 amps off the wall. Sadly, this engineering requirement was not passed. The system must have a user-adjustable maximum volume setting which limits the maximum volume output from the system for safety purposes. This engineering requirement was passed. The system must also be able to mute itself softly within 1 second. This requirement was also passed. The system must be powerful enough to drive 4 ohm speakers at 50 watts continuously into 5 channels. This requirement was passed. The system must have a total harmonic distortion rating of less than 5% at 1 watt to maintain audio signal integrity. This requirement was passed.
Okay, what we have here is our simplified block diagram, as opposed to the more elaborate one which we will discuss next. For the simple one, we have the audio input, which is our 4 primary inputs coming off the back of the system. From there, those go into the input selector. The input selector is a simple magnetic relay system, which through the digital controls allows the end user to select which input to be bypassed to the system. From there, that passes into the volume control. And the volume control is it's a digital chip which allows the user to attenuate the volume to an accuracy of half a decibel per click. And that, of course, is controlled then by digital controls and the end user. From the volume control, we go into the equalizer. The equalizer, like we discussed before, simply allows the end user to tone control or manipulate 3 individual bands, low, medium, high, up or down 6 decibels. This is also bypassable by the end user, which is not clearly shown here, but we'll discuss that later on. That goes into the audio amplifier, which of course amplifies the signal to an audible level and out to the speakers. Now, the audio amplifier does require a higher level of power, so we've specified that the audio amplifiers have their own separate amplifier power supply for their specific power requirements. And finally, what we have here is the DAC, the digital to analog converter. This had the job of taking in a digital source from, say, a USB or coaxial input, and then converting that to an analog signal which could be passed to our system. We were not successful, however, in making this block work, which will be discussed later on. From here we go to the more elaborate block diagram, which, as you can see, is a more detailed representation of our system as opposed to the simplified one. And we will discuss each of these parts in more detail in the next section, but for now, down here we have our digital controls. In the middle here, we have the equalizer and the digital to analog portions. And then along the top, we have the amplifiers and the output to the speakers.
To begin our detailed study of our block diagram, we will start with the 120 volts AC wall outlet. This is directly connected to two components of our audio amplifier system. The multi-purpose power supply, which powers various analog and digital elements, which Matt and Jesse will detail later, and the power relay. The power relay takes a digital signal input from the Atmega and, when enabled, forwards through the 120 volts AC through to our three amplifier power supplies. These amplifier power supplies will supply 27 volts and up to 5 amps to our three amplifiers. Our amplifiers are Shure Electronics Class D stereo amplifiers. The output of the amplifiers is quite obviously our amplified audio, which is played over the speakers. The subwoofer has its own built-in amplifier, so we forward unamplified audio to it. The inputs of the amplifiers are simply our unamplified audio. Now, Matt, to you to discuss the analog and digital design portions of the project.
Thanks, Scott. The multipurpose power supply provides useful voltages to the rest of the system, while the digital and analog signal processing portions of the system change the way the system interacts with our analog signal, which includes the equalizer and the volume control blocks. The equalizer block controls the signal's primary frequency bands and attenuates the gain at those specific bands, whereas the volume control block increases or decreases the volume of the signal as a whole. The equalizers can be bypassed using our equalizer bypass block, which drives the signal out of the volume control block straight to the amplifiers to increase signal fidelity. Now to Jesse with the digital controls.
Thanks, Matt. For the digital controls, everything centers around the Atmega 128 microcontroller, which is programmed via my code, which is compiled in the GCC compiler. The Atmega 128 is connected to a number of system blocks, including the power relay, the input selector, equalizer and equalizer bypass, volume control, as well as the various inputs. For the input selector, a 3-pin signal is sent to the board to determine which relay to turn off and which to turn on, allowing it to determine which signals to pass through to the system. For the equalizer and the volume control, there is an SPI signal, serial peripheral interface, which controls the digital pots here and the digital ICs here, which attenuate the signal as well as control the overall system volume. There is a 1-pin signal that goes to the equalizer bypass that determines whether or not the system should bypass the equalizer for increased fidelity or whether it should have it on for attenuation of those frequencies. For the inputs, there are 4 primary buttons: the power button, the input buttons, the mute button, and the equalizer selection button. power button simply turns the amplifiers on and off. The input buttons, which there are actually 4 of, control which input the system will receive. The mute button controls the soft mute functionality, which attenuates the signal smoothly down and smoothly back up as the system is muted and unmuted. The equalizer button, which controls whether or not the equalizer is bypassed or used. And then there is the volume knob, which of course controls the volume, and the equalizer knobs, which attenuate the different bands of the equalizer when it is in use. And then of course we have our power indicating LED to show that the system is running, and a display for system statuses. And now we will go to the next section. Of our engineering requirements, we were able to pass 8. However, there were 2 engineering requirements we were not able to pass. First off, the DAC, and secondly, our 6 amps from the wall requirement. Matt, would you like to discuss the digital to analog converter?
The DAC block was not passed primarily because of time. Because of PCB design and transportation delays, we simply did not have time to devote to the digital analog converter, and therefore it was not passed.
Thanks, Matt. Scott will now come in and discuss our 6 amps requirement and why we're not able to pass that. Scott?
Thank you, Jesse. We did not pass our 6 amps from the wall requirement simply because we had a poor power supply design. We used linear regulators, which are notoriously inefficient. If we had used a buck converter, we would have been golden.
Thanks, Scott. We'll now go to our system demonstration.
The project interfaces using these buttons and knobs on the front panel. The power button turns the system on and off. These are the input selection buttons, which allow us to select our different inputs. Our maximum volume setting button, our equalizer bypass button, the mute button for the system, as well as our volume control and equalizer settings. And the system goes up to 5.1 channels, but we are currently showing 2. I am now going to demonstrate the volume. As can be shown, it's playing music. I'm going to turn it up. As shown, we can attenuate the volume. I'm now going to move to the back side. This is the back side of our system, in which you can see the inputs of the system as well as the outputs of the system. The system has 2 dual channel inputs, its multi-channel inputs, the digital inputs, and the 1/8" audio dual channel input. The outputs of the system are the subwoofer output, the center outputs, the front left, front right, rear left, rear right, and these 6 make up the full 5.1 channel output, as well as the subwoofer. And that's our system. We now have some advice for incoming seniors. Scott?
Thank you, Matt. Our first piece of advice is to expect a drastic workload increase at the end of fall term, and it will stay increased until Engineering Expo. Be ready for it. Matt?
Also, you should be very specific on the wording of your engineering requirements. They will test you specifically on that wording, and you need to be careful about it. Jesse?
Yeah, I agree with both of those. And also, I believe that something that's not discussed enough in the program is the concept of grounding. And if you're going to be doing anything with any sort of high fidelity requirements like the audio product that we created, grounding becomes a serious issue because you're going to introduce things like ground loops, which create a great deal of noise in your output signal.
That concludes our final presentation. Thank you for watching.